Okay, so next we're going to look at a really common specific heat capacity question that combines it with the power formula. So we've got one to do together and another for practice, but they're quite easy to find because, as I say, they are very common, these ones. So in this question, in the bit I've cut off there, it sort of sets the question up, and you've got a piece of titanium, piece of metal there, and they're firing a laser at it, and that heats the titanium to make it melt because they're welding it to something. So we've got a piece of titanium and we're heating it by firing a laser at it. This is the energy of each photon in the laser, and this is how many photons per second are hitting it. Right, so if we're heating something up, that tells us straight away that we need the specific heat capacity formula. And so now we look and see, do we have the things that we need? So the mass of titanium, we aren't told, so we're going to have to work that out somehow. So we need to spot that we have got the density of titanium there, and we've also got the volume that's being heated. So the first mark is going to be for calculating the mass. So there's the density formula. So that means that density times volume is mass. So that's the mass, and that's our first mark. The next thing we're going to need is the specific heat capacity, and we have got that. And finally, we need the change in temperature. We're not told that, but we can calculate it. And so now we can work out the energy needed to melt this piece of titanium. And that's our second mark. So we now know the energy that we need to melt the titanium, and we're looking for the time it takes to melt it. And the formula that relates energy and time is, of course, the power formula, where W there is the energy transferred. So for us, the power of the laser beam is going to equal the energy transferred over the time, and so the time is going to be energy over power. So what we need is the power of the laser beam. And so what's that? Well, we've got two numbers left. We've got this many photons arriving every second, and they're each carrying this many joules of energy. So that's this many joules times this many photons arriving per second gives us 11 joules per second, and that's a power of 11 watts. And so finally, I'm afraid we don't get a mark for that. And so finally, we find our time. We need this much energy transferred. The power of the laser beam is 11 joules per second, and that gives a time of 2.8 times 10 to the minus 3 seconds. So that's 2.8 milliseconds, which of course is very, very small. And the next part of the question is equally common. It always follows on, because the next part says, in practice, it's going to take longer than that. Explain why. Now the standard one here, the standard mark, is that it's only one little area of the titanium that's being heated here, so some of the energy is going to transfer into the rest of it. But in this case, the second mark, it's a laser beam that's doing the heating, so these are photons coming in. So the second mark is that some of the photons will bounce off the titanium. Okay, so there you have it, your question where you're combining the specific heat capacity formula with the power formula, and usually working out the time, and then why does it take longer. All right, pause the video and have a go at another example. Okay, here we go, and it's a show that question. So remember, you're going to write out your unrounded answer and then go, oh look, it's about 5,000 watts, to show that you actually did the calculation. Right, so this time we're heating water in a shower, And so once again, we're heating water up to some final temperature there. And so that means we're using, once again, the specific heat capacity formula. Okay, so we've got the specific heat capacity of the water, that's there. So we've got this one. And then the change in temperature we can do, because there's our final and initial temperatures. We can do that one, but we haven't been given the mass. We've got to, once again, we've got to work out what the mass is. What we're told instead is the density and the volume per unit time. So then, I know this is not the best diagram, but if that's your shower, you've got to imagine it's this volume of water. So every minute, this volume of water coming out is 3.60 times 10 to the minus 3 meters cubed. So in 1 minute, that's how much comes out. Well, we can work out what the mass of that is, because mass is once again density times volume. And there's the density of the water, and this is the volume that we're using. So this is the mass of water coming out the shower in 1 minute, so in 60 seconds. And that means we've used this piece of information as well. Okay, so we've got our mass now, so we can use our heat capacity formula. So we've got, there's the mass times the heat capacity, specific heat capacity, times the change in temperature there, and that comes out as, obviously we're not rounding anything yet, so it's that many joules to heat this much water. And remember, that's how much comes out in 60 seconds. Okay, and so finally the power is the amount of energy transferred divided by how much time it takes to transfer it. So that is that much energy we said every 60 seconds, which is this, and that is about 5,000 watts. Now, I know I said normally it says why does it take longer, and it's all about energy being lost to surroundings. This one's slightly different. This one's saying we've just worked out the power of the shower, the heating element. What might have given us a different value for that? And so the two things that they are looking for, very unusual this one, the two things they were looking for is that the rate of the flow of the water might change. In other words, that number might change. Or the other thing is that the temperature the water comes in at might change. So they're saying that this one here might change. Those were the two things they were looking for. So if you get a question like that, just have a really good think practically. Think, sort of almost put aside your physics and just think, okay, in the real world, what would actually be affecting this? Okay, but in general, remember, you've got your heat capacity formula, you've got your power formula, and then you're combining them.